It's time to learn about limits at infinity. Let's first go back to limits equal to infinity, which show up in a case such as 1 over x squared, where the function has a vertical asymptote at x equals 0. When there's a vertical asymptote, we're talking about one of these two limits. Actually, I'm lying a bit here, since we really only need a one-sided limit equal to infinity to have a vertical asymptote. But what about horizontal asymptotes? If we just switch a and infinity in the equations for vertical asymptotes, then we get these, which are the ones for horizontal asymptotes. We'll see a similar parallel between the definitions of these types of limits too. Let's look at an example to motivate the definition. This function, as it goes off to the right, seems to settle closer and closer to some value. Let's call it a. More precisely, we can put a band around that dotted line as narrow as we want, and there will always be some x value beyond which the function never leaves that band. That's the essence of the definition of a limit at infinity. To say that the limit of f of x as x goes to infinity, or as x approaches infinity, is equal to a means that for every epsilon greater than 0, there's an m such that the absolute value of f of x minus a is less than epsilon whenever x is greater than m. There's a similar definition for a limit as x goes to negative infinity. Going back to the graph with the band, here's where epsilon is. It's half the width of the band. And right about here is where m is, because beyond that, the function never leaves the band. Let's take another look at the parallels between vertical and horizontal asymptotes. And once again, in the case of vertical asymptotes, we really only need one-sided limits. For convenience, let's only consider positive infinity. For a vertical asymptote, we have a limit as x approaches a, and that's equal to infinity. For a horizontal asymptote, we have a limit as x approaches infinity, and that's equal to a. And here are the definitions, which have the same parallel. The m and delta in the first case switch places to become epsilon and m in the second one. Let's look at an example. Let's let f of x equal 1 over x. Then the limit as x goes to infinity is 0. We knew that already from the graph. We could actually make the numerator any constant without changing this limit. In fact, we could do even more than that, but that's a topic for another time. And there are more examples of limits at infinity in the example video. But what if this limit doesn't exist? Just as with the case of a limit at a real number, many things are possible, but there's a special case where the limit's equal to plus or minus infinity. Some examples we know of because we know what the graphs look like. For example, e to the x, which goes to infinity as x goes to infinity, 7 minus x squared, which goes to negative infinity as x goes to either plus or minus infinity. We know that because this is a quadratic function with a negative leading term, so the graph is a parabola that opens downward. The square root of x, and the natural log of x. These last two grow fairly slowly, but they still go to infinity as x does. The formal definition of a limit at infinity equaling infinity is, I hope, not a surprise. It means that for every m greater than 0, there's an n such that f of x is greater than m whenever x is greater than n. Looking at a picture of e to the x, for example, this really just means that the function goes up this way. Another type of non-existence is oscillatory behavior, as we see with this sine-like function. We can choose a band like this that's narrow enough so that no matter how far you go in either direction, the function always escapes it.